Okay, all right. So we will try to cover, I guess, two topics if we can, okay? Because the first one is causality is relatively short. Okay, you will see that. We're gonna work one more example of causality, and now in practice doing it with Python as well. Okay, so that involves, as you will see, understanding why it is an experiment, right? And then that is why you are able to create causality statements in the end. Okay, but then more importantly, we're going to see an example where we actually have the data, right? We're able to set up hypothesis. We're able to figure out like a test statistic that we want to do. And then of course, the actual simulation part, and then the p-value decision-making process. Okay, so that's for this causality topic that we want to cover. So let's get started with that. In the meantime, I guess we're also going to do some kind of quick review from before a little bit as well. Okay, so for causality here, okay, we are talking about randomized controlled experiment. Okay, so the term now hopefully starts to make more sense of why we're not just calling it an experiment for short, but like randomized controlled experiment. Okay, we're gonna walk through this concept one more time and then see it in a example now. Okay, so it's about low back pain. Okay, there is a particular treatment that could be useful. So it's botulinum, I think, toxin A. Let's just say BTA for short. I'm not really good at pronouncing those hard words. And okay, so the treatment, okay, is this particular mat, okay, and then people are curious about whether it's going to be an effective treatment for low back pain. Okay, so since I think from early on in this semester, we know about how we're able to go about doing this comparison, if you remember, okay? And then in particular for experiment, we're talking about two groups, okay? Now I think we know by heart, we have a control group and then we have a treatment group, okay? And in this case, I would say the treatment is pretty clear, okay? It's gonna be the BTA MAD itself, okay? So later you will see that, well, once we come up with the groups, how exactly we're gonna see how, but once we come up with that, then the treatment itself gonna be the BTA MAD itself, okay? So this does, like when I was preparing it, I do want to go back really quick to, if you remember last Tuesday, I'm just showing the topic 15 lecture slide really quick. Okay, I wanted to bring back to that example, if you guys remember about the gender discrimination, right? I was describing the setup and then we are looking at a table. And then remember, I asked a question about whether this is observational study or experiment. Okay, and I think, I guess maybe I was the only person thinking this is experiment, and everybody else sort of coming out of the breakout rooms. You guys were saying it's more like observational study. Okay, so I remember back then, so I can think now it's a good time to revisit this really quick as well. Especially here, I would say that I guess last time we were able to identify, at least to some degree, that it was randomly determined, right? So we do have the randomization. This is a term that we're going to start to use a lot more often now. This is the randomization process of putting people in different groups. Okay, so this I think is one key aspect or a key characteristic of doing experiment. But I do want to come back to this exercise or example really quick as well, mostly because I think last time I was saying in this problem, there's no like a clear treatment that we're talking about, right? And I guess that's why it was a little bit challenging to determine whether this is actually experiment or not, because as we are seeing in the causality example here now, we're really talking about like you do have a treatment, right? And then you give it to the treatment group, right? And then the control group does not receive that treatment. So it's a little bit, I agree, unclear, I guess, or like a little bit implicit in this example. So if we really think hard about this gender discrimination, okay, we have two groups, right? One group clearly is just a male group, right? The other one is the female group. So here, yes, we do have a treatment and control group, okay? It's not that we're actually gonna give the treatment to the people in the treatment group and do not give the treatment to the control group. It's more about exactly what that we're testing for. And that's how we design those two different groups. Okay, so here we're testing about gender discrimination, okay, if you remember. Then that's why here, even though there's no like a medication or whatever involved, but this is experiment, because we randomize those observations into two groups. And between the two groups, pretty much the only difference between them is about the gender. Okay, so this is hopefully can clear up some of the confusion if you still have any, okay, especially back about this particular example. So I just want to say that for our BTA example that we're doing today, well, clearly there is a treatment. So, and we know that we're doing experiment and all that. So it's pretty clear. But going back to that gender discrimination example, I just want to say that not every time you're going to get an actual treatment going on. Okay. But a better way, I think, or like a more general way to think about treatment is, well, I have two groups, right? And then I really want to, I do the randomization or like randomly assign observations into the two groups. So I will only have the difference about the groups themselves, I should say, about the observations in those two groups. They're similar except for the groups themselves. Okay, so then for the gender discrimination example, they are all the same, right? Remember the example itself, they say like it's the identical, the same personnel file, right? And the only thing that is different is about the gender of the applicant or I guess the employee. Okay, yeah. So in that case, it is still an experiment. Okay, even though there is no clear treatment going on, we are not giving a treatment to any of the group. Okay, but you are still testing out about the gender aspect of things, so you will still consider it as a experiment. Okay, so I hope the detour makes sense overall, but let me know like in the chat or just like speak up if you have further questions about categorizing that gender discrimination experiment. But here I hope, I hope for this BTA example is pretty clear overall that we're doing a experiment over here. Okay. All right, so coming back here, okay, we have two groups. Okay, now one of them is control, the other is the treatment group, and clearly we're going to give the treatment group the BTA medicine, I think, and then the other one is probably some kind of like non-effect, or like sometimes you probably have heard about the word placebo group. Okay, so you're still going to give the control group something, okay, just to make sure that you can eliminate any kind of like psychological effect that somebody thinks that they're taking like a medicine, so everything seems to improve. I think, I mean, I feel that all the time, but anyway, it's human nature. So I think that's another reason why people try to make sure that is happening. Okay, so all right, good. Now if I come back to this example, okay, and just to refresh all of our memory one more time, if the treatment and the control groups are selected random, meaning that we're randomly putting observations or subjects in each of the groups, okay, then if you're able to come up with any kind of conclusion after doing the hypothesis testing, you will be able to make causal conclusions. Okay, so this again, in the past, we know that if you're doing an experiment, right, randomized controlled experiment, you will be able to make causal conclusions. Okay, now we're making it a little bit more specific. Okay, that what do we really mean by a randomized controlled experiment? Okay, now we have known all of the terminology, the experiences, and the exercises that we have done, examples. So here we're being very specific. Okay, if I do have two groups, okay, and we are able to make sure that the observations are selected at random into each of the groups, or we also call it randomization or randomized, then you can make the causal conclusions. Okay, so nothing very different from before. We're just being a little bit more precise given what we have known already. Okay, alrighty, so now I have two groups. Okay, so now I'm gonna start doing testing. Okay, we're gonna walk through this example together. Okay, but before we get that, we know that like for any kind of testing, based on the framework that we have been talking about, like the hypothesis testing, like a null hypothesis and the alternative hypothesis, where the null is representing the status quo, right? The other one is the alternative, okay? So remember, we always come up with two. Of course, in later, not in our course, but in the future, you might come up with multiple, that's totally fine. And, but for us, we restrict ourselves to talk about two. One is the null, the other one is the alternative. And then here, because of the randomization step that we're able to enforce, then any difference in the outcomes, okay, now, between the two groups, okay, could be due to two types of resources, okay, sources, I should say. The one is the chance model, which will be our null hypothesis, if you remember, okay, or it will be due to the treatment, which is usually referred to the alternative hypothesis, okay. So remember, these are the two viewpoints, right, that we started talking about in the first place, and then later on, we turn those viewpoints into hypotheses, where the null hypothesis is usually the chance model, right, that you're able to simulate data under from. And then the alternative will be, in this case, the treatment that you will be able to test for. Okay, so and one more time, I guess just to repeat it one more time here, we highlight any difference in the outcome between the two groups could be due to, and this is because we are able to attribute to either the chance model or the treatment model because we have done the randomization, meaning that the two groups, the observations, they're very similar to each other except for the treatment or the control group assignment that they're doing. Okay, and it is indeed because of that, exactly because of that, we're able to do this hypothesis testing and later on come to a causal conclusion. So keep those in mind, okay? We talked a lot about different aspects, and I'm sure I repeat myself multiple times on certain concepts, but just to make sure that we're on the same page and then we're ready to go to a demo together, which hopefully will make things much clearer, okay? So this is the first demo for topic 17, okay? So if you open that, not now, but if you want to, feel free, and then we're gonna do a randomized control experiment with the BTA data, okay? So the BTA data should be loaded for you in the space, okay? So let me see. Yeah, I don't know how many, I should I should know better. Oh, I think, wait, yeah, there are 31, sorry. There are 31 observations in total, okay? And then the data set, as you can see, has two columns, right? The first one is the group assignment. We have the control, and then we have the treatment, okay? And then the result column is a binary, like a Boolean, okay? If it's 1, meaning that it does improve the outcome, the lower back pain, okay? If it's coded as 1. If it's coded 0, meaning that nothing is improved, okay? So these are the two variables here. Both of them are binary in some sense, right? Like the group is either control versus treatment, and result is 1 versus 0. Okay, but 1 means that somebody has seen improvement of lower back pain. 0 is no improvement. Okay, so this is how the data looks like. Okay, and you will see soon that, well, remember, before we're doing any kind of simulation, right, we always wanted to think about, say, if we're going to come up with the test statistic, right, in the end, we always need to also get the observed statistic from the data set, right? So remember, in our usual procedure of doing hypothesis, you come up with hypothesis, right, the two, and then you come up with the statistic that you think is the best, or like among the best to test out your hypothesis. And then you're going to simulate the data, right? Simulate data under the null hypothesis for a large number of times, right? Each time you're going to compute the test statistic. And then in the end, if you remember, we get the p-value, for example, or some other, if you want, like maybe just simply compare them. But p-value is a good way to evaluate how likely the data that you observe is under the null, okay? And so, like, I know it's the last step that we do, but it's also good for us to just to refresh our memory. That whenever you get a data set, even before you are thinking about how you're going to do the simulation for the hypothesis test, you should think about the test statistic that you want to work with, okay? And then on top of that, you should figure out how to actually get the test statistic from the observed data, because whenever you're doing simulation, you have to do it on the simulated data, so it's probably the same set of process, like same set of code in particular, that you're able to get the observed statistic as on the observed data, just like the test statistic that you will be able to get on the simulated data, okay? So for us, okay, so there are multiple things we can do, especially now, I guess this is also like a quick review as well. Now we're working with 2 categorical variables, right? Both are binary. And so we should be able to do some summary about them. Okay, and in particular, you will see that we're trying to get the average treatment outcome between the treatment group and the control group. Okay, so the way that we're going to get it. So first of all, just to verify that we do have 2 groups, right? And then we have 31 observations in total. Among them, 16 were in the control group, and then 15 were in the treatment group. Okay, so if I do the dot group method, right? And then include the quote, include the column name or the label name in the column in the quote in the method group method, then I should be able to return the counts, right, of each different groups. Okay, so that's only for one categorical variable, right? If I want to do like cross tabulation, if you remember the pivot method, okay, and in this case we do have group and result, 2 categorical variables. So if we use both of them here. Sorry, yeah, don't worry about those warnings. It should be fine. Like it would just work just fine. It's just a data science package thing. but the outcome should just look fine to you. So here we have a cross tabulation, right? We have the group assignment, okay, like showing over here. But at the same time, we also have the, if you remember the outcome, one is 0, the other one is 1 for the result. Okay, so this gives us a tally of the counts of each cross tabulations over here. But then of course, we can always use the group method to get the average. So this is the test statistic later on that we're gonna work on. Also, in particular, I'm doing the, as you can see, the group. Okay, the group method is being applied to the group column, but then I'm summarizing, right, the result. And in particular, I'm summarizing it in terms of the average. Okay, so if you look at this output here, I have the group, 2 groups, right, control and treatment. I'm having the result average of the control group is 0.128, okay, and the treatment group is 0.6. Okay, so this is one test statistic. Okay, you can maybe work with other ones. We can maybe do a breakout room soon to think about it, what else you want to do. But pretty much this one, what we're interested in is that you remember if somebody has seen improvement, it's coded as 1 in the result column, right? If it's no improvement, it's coded as 0. So if we're able to get the average result outcome, right, among the control group and then also among the treatment group, and if I take the difference of the two, which in the observed data is 0.475, that gives me a sense, right, of how large, like how different on average, right, the result is between the control treatment group and the control group. We're seeing a, I don't know, it's hard to tell, right, whether 0.475 is large or not. That's what we're going to find out later on, okay? But this is showing us, like in the observed data, right, on average, we see that the average result of the treatment of the experiment, I should say, of the control group is 0.475 lower, right, than that of the treatment group. Okay, so for us, if we come back to the slide really quick, okay, like I said, we will do in our experiment, you will see soon that we're going to do the randomization. And then, of course, any kind of difference due to the outcome going to be either due to the trans, which is the null hypothesis, right, or the treatment, which is the alternative hypothesis. So for us, we are one step closer to that, right? Right now, we know how to get that test statistic in place and then how to do it on the observed data. Okay, so you will see that, well, from last lecture, I think there is a, last Thursday with Jason, I mean, there is a function sort of that we're able to get the difference of means. Okay, so here I'm showing it just because we can wrap it up as a function, so it will be much simpler later on to try to get the difference. Okay, and you can imagine, well, now I have written this function, then later on, I will be able to put that as a function into my loop, right? Then everything will work much faster. But let's walk through this like function really quick. But I just want to show you that the observed difference can be computed using this function, right? Like it's 0.475 up here when we do it step by step. It's going to be the same down here after I use this function. Okay, so the function, if we come back here and you will see that it takes 3 inputs. Okay, the data table itself, okay, the label, which is the label that we're gonna be focused on, in this case, like the result label, okay, and then also the group label, that is the label or like the column about the group assignment. Okay, so what we're doing here, as you can see, is that we're gonna take the name of the table, the column label of the numerical variable, and the column label of the group label, which is gonna return us the difference of means of the 2 groups. Okay, so we can definitely, let's just spend time to look at the few lines more carefully, but definitely make sure that you revisit this to make sure that you understand why we're doing this. And once you do this, like once, I think it will become pretty clear and pretty convenient that you're going to use this all the time, I think, for all of the other simulation that you're going to do. Okay, so so what we do in this function, as you can see, is that yes, we started up with the table, right? Like a multiple columns. In our example, only 2. That's great, but sometimes you might have multiple seemingly irrelevant columns for us in terms of what we try to do. So maybe the first thing we can do is to reduce the larger table only to the 2 columns that we're interested in. Okay, and the reason, if you already thought about it, is that here, if you remember, right, like I'm doing like the botox.group, right, and then use the group and then the MP average. And it's nice because I only have the result, right? Result is the only numerical variable that I'm interested in. And so I'm only going to get the average of that particular variable, right? But imagine you have some other ones, and then you start to get so many different summaries that might not be necessary for you to know. And I think that's the main reason why in this particular difference of means function that we're writing, we're trying to reduce it. The first step, as you can see, is reduce the table with the 2 relevant columns only, okay? Because later on, when you do the summary, that will be much easier to deal with, okay? All right, so we get the reduced table, okay? That's using the select method, okay? We are selecting the 2 columns, and then we're still gonna have a data table in the reduced object, okay? And then we're gonna do the group method, okay? So it's being done on the reduced object, okay? And then, which is a data table. And then you're gonna you're gonna supply the group label, which is like control and versus treatment, like what we did. And then the second one is, in our case, is always sort of like the NP average, okay? Because we're looking at the difference between the two. And then lastly, we're returning like the second item minus the first item, and then we're able to get the difference. Okay, so if you use this function, like you write it once, right? And then you can use it on the observed data, great. And then later on, you can use this function in the simulation when you're doing it for a large number of times. Then you can be sure that every time you're getting the same quantity, like the same concept of the quantity that you're doing. Okay, so always the second minus the first. Okay. All right, hopefully that makes sense. And like I said, this is similar to a function that we you guys did with Jason last week. But here we bring it back mostly because this could be really handy later on. But regardless, all of this is trying to help us to get the test statistic, right? And then compute the test statistic under the observed data. And that will always be important for us later on to come up with the decision, especially you're going to use it for coming up with the p-value. Okay, make sense overall? Okay, all righty, great. Okay, now let's talk a little bit more about what are we really doing here for doing this particular experiment for causality. Okay, so here, let's see, let's just do like imaginary thought exercise over here. Okay, so before the randomization, okay, you can imagine that like each participant, so there are 31 of them, okay, in the experiment, each one has a ticket, okay, and then like it's two parts, okay. The one is that what if it's like the person or like the subject is assigned to the treatment group, the other one is the person is assigned to the control group. Okay, like say, because at this point, if you remember like the randomization, if you remember like the process doing this is that you put all of the observations together, right? And then you randomly select which one to go to which, okay? So it's almost like, you can imagine like a ticket, like here, everybody gets like 2 parts, right? You have either, you could be assigned to the treatment group, you could be assigned to the control group, but we don't know which one it is, okay? And then for us, you can think of this like as how, before the randomization starts, how each person is participating, okay, in this experiment. And then, of course, after we do the randomization, okay, each person is only being assigned to one of them, right? And then you're going to receive the data after they either go through the treatment or the non-treatment process, okay? So what happens in our study here is that among 31 subjects or participants, 16 were randomly picked the tickets to go to the control group, right? And then the remaining 15 were like whoever were not picked, right, going to be assigned to the treatment group. Okay, so in the observed data, okay, what we are seeing is that 16 are in the control group and then 15 are in the treatment group. Okay, it's 31, so it's you know, it's odd number, so you're just going to do your best to like evenly divide it. Okay, so in this case, we have 16 in the control and then 15 in the treatment. Okay, so imagine like now the tickets is almost like, okay, so for all of the ones being randomly selected to the treatment, to the control group, it's going to be the one showing on the top, and to the treatment group is the one showing at the bottom. Okay, so just imagine this going on. Like I guess it's important for us to think it through, like how the randomization is really doing. Okay, so like the ticket idea is one way to hopefully like help you to distill that thinking of doing randomization. Okay. All right, so with all that in mind, let's get ready to test the hypothesis. Okay, I will go through, I guess, if you remember the 4 different steps, right? We come up with a hypothesis. Okay, we need to know what it is, the null, what is the alternative, and also what else? Like think about the test statistic, right? And then also you will have to do the simulation under the null, right? And then lastly, you're going to use the p-value to do the hypothesis, okay? Testing, I should say, okay? So yeah, I think let's maybe take a moment for you all to go to a breakout room just to talk through. I know I already listed all of the like the write-up over there, so maybe ask yourself not to watch it, but just like think about the problem in hand that you are able to talk through the process with your team members really quick and the breakout room members really quick, and then we come back and then we continue with the demo. Okay, so let's do that for a short, for quick. Okay, welcome back, and I think pretty much everybody's back. Maybe just a couple of you coming back from the room, and let me in the meantime restart sharing my screen, so we're gonna see the same thing together. Okay, all right, so since yeah, I hope everybody got the chance to discuss quickly what you think are necessary for testing the hypothesis. So in that case, I'm just going to show you, I guess, the entire slide in one show, but let's talk through them. Okay, like I said, I think overall, they're similar to what we had done before, but I do want to bring your attention to the null and the alternative hypothesis here a little bit. Okay, so the ones that we're setting up over here is that the null hypothesis is that the distribution of all 31 potential control scores is the same as the distribution of all 31 potential treatment groups, while the alternative is saying that they're different. Okay, so remember in the past, when we're not comparing two groups, okay, we're just like saying, like say the jury selection example, we're really having the null hypothesis, like what we observe, or I should say like the jury selection is representative, right, of the population racial breakdown and stuff like that. So you always sort of like have something that is there, like about the population that you're able to compare to. So in those cases, the null is different, right? Whereas here, okay, when we're doing an experiment, like I said, we have 31 observations in total, okay, and we were supposed to randomly select them into two different groups and stuff like that. So because of that, our null hypothesis, okay, we are framing it in this particular way, that if we imagine like all of the 31, right, like they are either potential control scores or, right, the potential treatment scores. So the null hypothesis is saying that for all of them, either like one group of the control, the other one is the treatment group, the distribution of the score is going to be similar across the two. Okay, whereas the alternative, and that's the chance model, right? Like it's whatever being randomly selected is just by chance the difference that we're seeing. Whereas the alternative is saying that the distribution of the 31 potential control scores is different from that of 31 potential treatment scores. Okay, so this I just wanted to highlight because like I said, this is in some way similar to the A/B testing that we covered last week as well. Okay, but then in this case, we're doing experiment, right? So we are thinking about potential scores. All right, and the test statistic hopefully makes sense to you now as well, especially just now in the previous demo, I showed how we are actually able to compute this statistic from the observed data, okay? And in this case, the test statistic is the treatment group average minus the control group average. And remember, when we're picking a statistic, we want to pick a statistic that, like say, if it's large, then it will favor, right? The alternative, it's small, it will favor the null. So in this case, because the treatment, if you remember, like the result column, if it's one, it is one. If somebody did see improvement, if it's zero, it's no improvement. So larger value of the difference of the average here gonna favor the alternative, okay? Meaning that the treatment, right, is helping more than the control, or like no treatment, okay? Alrighty, and then the third step, which we're gonna see how to do it in the demo in a second, okay, simulating on the null, right? Okay, and then this one is gonna be very similar to the previous ones that we did, okay? We're actually shuffling the group label, okay? So we're able to maintain the two group sizes and then find the difference between the averages of the two shuffled groups. And then we repeat that for a large number of times, okay? So this is what we mean by under the null, right? Under the null is saying that, well, the distribution of the control scores is the same as the distribution of treatment scores. So that means under the null, if I want to simulate under the null using the data set that I have in the observed data set, then what I'm doing is I'm merely just like shuffling the group label, okay? Because I'm controlling the group size, and then whatever the differences we're seeing, right, is due to chance. And that's what we mean by simulating under the null, okay? Lastly, we are able to compute the p-value. We're gonna see it again in the example. And then you can either use the 5%, which is what we call statistical significant level, right? Or like highly significant level, 1%. We can see which one we wanna use, and then for this particular example. Okay, so let's come back to that hypothesis testing. So that's a new notebook. Okay, so take a look later on. Okay, all right, so load everything. Okay, and then I also load the difference of means. That was the function that we talked through earlier. Okay, this is like you have a larger table and then we reduce it to a smaller table, and then we're taking the difference of the means of the two groups. Okay. All right, so this function, you will see that we're going to use it again. All right, so the data set again, okay, I loaded it one more time, okay, and I'm using the difference of means. That's the function that we loaded earlier. So I'm able to get this 0.7475, okay, so that's the observed difference, okay, if you remember, okay. All righty. So now notice, of course, you can, I think it's probably always easier if you are able to write something along the lines of one simulated difference, okay, that you're able to wrap it up in a function. So later on in your for loop, you're able to just call it, and then you can remember append the outcome to the array that you started with. So in the end, you're able to get a bunch of them. So you're able to do your hypothesis testing. Okay, so here, let's see. So I'm writing it as one simulated difference. Okay, so this again, as you can see, simulation is involved, right? So as you will see, we're going to do a sample method again, and then do all of that. So in this case, I'm also have, I guess, yeah, I'm having 3 inputs over here, right? The table, okay, that's the name of the table. And then the column label of the numerical variable, which is the result column, right? And then the group level, group label, which is the column label of the group level variable, okay? It's gonna return me the difference of means of the two groups after I'm shuffling the label, okay? All right, so how am I supposed to do that? So the first step, as you can remember, is to create an array of shuffled labels, okay? The way that we're doing it, if you remember, is that we are taking, right, with replacement, without replacement, sorry, because we wanted to make sure that like the same sample, like the group sizes stay the same, right? Still we're gonna have 16 control labels, right? And then 15 treatment labels. So to make sure that is happening, we're doing without replacement sampling, okay? And then we also only gonna select, or in this case, use the column method to only get the array of the group label, which is the shuffled version. Okay, so one round of this line, as you can imagine, is that, remember, we have 31 labels of the group, right, that we start with, right? 16 of them are the control, 15 of them are the treatment. So we're like just shuffling them to have a new arrangement. Okay, so every time it's gonna give us a new arrangement. Okay? That's what we mean by the shuffled labels, okay? This is, again, similar to the gender discrimination example that we saw last week, okay? Alrighty, so once we get done that, then what we can do is to get the table of numerical variable and the shuffled labels. Okay, so what we're doing, as you can see, is that we're gonna get a table, right? We select the label, which is, in this case, the input of the numerical, the name, right, of the column of the numerical variable. And then we also gonna attach it, right, with our shuffled label. Okay, so that is gonna be a table of 2 columns, right? The label itself, the variable, the result in this case, is as the first column, and the second column is the shuffled labels. Okay, so we're gonna get 2 of them, and then of course, then we're able to use our already written function of the difference of the means, right? So in the end, we're able to return the differences of the average across the 2 groups. Okay, so the steps, again, I think definitely worthwhile revisiting if you find a little bit like too much going on. But in class, we try to talk through them, the reasoning why we do this. But then a lot of times, I think it does make sense for you to revisit. And for us, let's see, once we are done with writing that function, we can just take one round of it. Okay, so this is giving me, so again, this is already simulation, okay, because we're taking a random sample, like we're doing the shuffling label and then get one outcome here. So it's about 21%, okay, or 0.21. If I run it again, it's going to be a different number. Okay, so that's what we can make sure that what we're doing is indeed random over here. Okay, so let me run the usual for loop. Okay, it's going to take a while. That's why I wanted to set it to run. I'm doing it for 10,000 times. Okay, so what I'm doing is that based on the BTA data that we have, okay, I'm doing it repeatedly for 10,000 times. That's what we mean by simulating under the null, right? Simulating under the null for a large number of times, okay? But each time, not only that I created like a new data table, right, with the result column and then the reshuffled group label, but also more importantly, I'm taking the difference, right, of the test statistic that I'm able to do, because that's what, well, we need later on if we're trying to do any kind of testing. Okay, so that's why I have that step over there. So just as before, now we have a array, right, of all the simulated differences of 10,000 of them. Okay, so now I'm ready to do a histogram. Okay, let's pause here to think about a little bit of what the histogram is telling us. Okay, so distance between the two groups, okay, under the null, okay, and let's see. So center of ground zero, I guess that makes sense, right? Because you're saying that the null hypothesis saying that the two distributions are the same, like regardless which group you're coming from, okay? And then under that, we can see the center at zero, relatively symmetric. I guess the most extreme on the positive side, we went up to 0.6-ish, right? And then the negative side is like -4-ish, okay? And we know that, now just to refresh your memory, the observed difference is 0.475, okay? So looking at the graph, we know that's gonna be, I don't know, somewhere over here. Okay, exactly where I guess it's better if we use the p-value calculation, right? To know that how many out of all of the 10,000 simulations that we have got some test statistic as extreme as what we're seeing in the data. Okay, so the typical approach, I think now with so many different exercises, you probably are pretty familiar with this now. We are, right, comparing the simulated differences with the observed differences, okay, in particular, because our observed is a positive value, right? So we're looking at the ones greater or equal to that, and then divided by, so we do the sum. So just one more time, I guess, this comparison over here gives us a array of the Boolean operators, right? Zeros and ones, okay? So for us, we want to know how many of them are zeros. So we, sorry, how many of them are ones. So we're able to do a sum over here. So that's going to give us the number of times out of that 10,000 times, we're gonna get a more extreme simulated difference, okay? And then we divide it by, well, up here we know that it's 10,000. So if you want to write down 10,000, that's fine. But you can also use the len method that's returning you the length of the array that you're computing. So this is more automatic, I think. So let's look at the p-value, okay? So in this case, it's 0.0075, okay? If I come back to our last step over here, we calculate the p-value and then we should make a decision. So feel free to speak up or just type in the chat instead of, I guess, creating a breakout room for a short question like this. Given a cutoff point of 5%, okay, are we rejecting the null or not? Yes, no. You can type in the chat or just speak up, whichever is fine that you feel comfortable with.
Can you ask my question again?
Oh yeah, sure, go ahead.
Sorry.
Oh, you mean repeat the question, sorry about that. Yes, I'm saying that we are getting a 0.0075 p-value, okay? And now if I come back to the decision-making process, okay? And remember, we can have two different thresholds that we want to use, okay? So my first part of the question is, if I'm using the cutoff point of 5%, do you reject the null or not, given the p-value here? And what does that tell us of the outcome? Anyone? You can type in the chat like yes or no of rejecting. So I guess if you think we're gonna reject the null, you can type yes. If you think we're not rejecting the null, you can type no. So maybe this is something we should maybe talk through one more time. how to make the decision. Okay, so we have a no question mark. Okay. All right. Okay. Yeah. Again, I think maybe, okay, sure. I will talk through again. Okay. So the p-value, okay, if you remember, let me see, which was the, yeah, it was the decision and uncertainty, right? So it's probably down here. Okay. Here, right? We're talking about like how we're making decisions in the end once we get the p-value. Okay. Yeah. So, alrighty. So if we come back here, and yeah, let's just use this one, or like maybe it's better to come back, I guess, to whatever we're doing over here. Okay, yeah. So let's use this current example. Okay, so the p-value, as we know, is computing, right? Out of all of the simulations that I've done, right? The percentage out of all of them of the simulated differences that we're seeing is greater or equal to, or maybe in plain English, as extreme as what we observe in the data. Okay, so remember, this whole hypothesis testing paradigm is set up based on the assumption that we're simulating data under the null. Okay, meaning that we assume that the null is true, right? We're able to simulate the data, and then that means we are simulating a bunch of statistics as well. Okay, and then the p-value is a probability. Okay, it's telling us that if the null is indeed true, how likely it is for me to observe something as extreme as what I observe in the data. So imagine, and that's what we're saying that we're trying to like look at like in the tells, right? Like say, if without the concept of p-value, if you remember, at first we're talking a little bit informally, right? We're talking about, okay, I wanted to simulate a bunch of test statistics under the null hypothesis because the null is saying that it is the null, like there's nothing going on, or in this case, the two are the same, okay? And then I have a bunch of them, and now I have an observed data point, which is 0.475 come along, okay? If it's in the bulk of the histogram that I'm doing, right? That is what we mean by it is consistent with the null, right? Consistent meaning that, well, if my null is true, well, it is very likely to come up with whatever I've seen in the data. Okay? However, if it's in the tell, okay, then we know that, well, it might be telling me that if I do make the assumption that my null is true, it is still very unlikely to observe what I observe in my data. Okay, and that's what we mean by inconsistent, right? Telling us that, well, this might tell me that my assumption about that the null is true might not be correct, right? Because if I make that assumption, I'm not very likely to see what I have seen in the data. Okay, that's when the data, the observed data, is in the tell. Okay, so that's before we started talking about p-value, if you remember that, like talking about like consistent with the data, meaning that it gives evidence towards the null. If it's inconsistent with the data, remember, we're saying that it's showing evidence towards the alternative. Okay, so with p-value, what we're doing is that we can quantify how likely it is. Okay, and the quantification happens in this way. Okay, so this is the distance between groups, if you remember, okay, for this experiment that we're doing. Okay, and then what we're doing in the computational p-value, if you look at it one more time, the simulated diffs, if you remember, that's the array, right, of 10,000. So that's what's plotted in the histogram, okay? What we're doing is that we're comparing each simulated difference against the observed difference, right? And in particular, I'm comparing and I'm returning Boolean zeros and ones, right? It's going to return a 1 if the simulated one of the like if this particular simulated diff is greater or equal to the observed diff. Okay, and then so that's what we're doing by the greater or equal to sign over here. Okay, so all of this, when I do this line, it's going to give me ones and zeros. Okay, if it is 1, then meaning that that simulation in particular gives me a simulated difference as extreme as the observed. Okay, it's gonna give me a 0 if it's not gonna be as extreme as the observed. Okay, and I do the sum of them, meaning that I'm only counting the number of ones. Okay, meaning that I'm only getting the number of as extreme as my observed difference. Okay, and then in the end, I'm dividing because I want a probability, right, out of all of the 10,000 ones that I've done. So I'm dividing that by the length. Okay, that's what the LEM is doing. Okay, And then that's what the p-value is. Okay, so p-value, if I repeat it one more time, is the probability that if the null hypothesis is indeed true, then I'm getting the probability that my I will get the probability out of all of the simulations that I have done that I will get a simulated diff as extreme as my observed diff. Okay, if that value is really small, that tells me that, well, I probably have evidence against the null, right? Meaning that it's very unlikely for me to observe something as extreme as my observed difference if the null hypothesis is true. However, if the p-value is large, well, how large is large? That's what we're talking about, the cutoff. Okay, so we're going to come back to that in a second. But just like to finish the thought here, if the p-value is large, then that is probably telling us that, well, your null is probably okay, because under the assumption that the null is true, it is overall likely for you to observe something as extreme as what you are seeing over here. Okay, so if I come back, okay, to this, once we compute the p-value, right, we're going to sort of like compare it to cutoff points. So the two that we covered before is, the first one is 5%, okay, that is what we call like statistical significant, okay, meaning that if you're using a cutoff point 5%, okay, if your p-value is smaller than that, that means that you have significant evidence, like statistically significant evidence against the null, okay? And then, so when p-value is smaller than 5%, you're going to reject the null, because the null is saying that they're the same, okay? But you're rejecting it because you have more evidence in favor of the alternative, okay? And then, and smaller cutoff point is this 1%, okay? So you can use that if you want to be a little bit more strict in terms of rejecting over here, okay? So I guess now, okay, this is a long detour over here. So if now I come back to my question one more time, okay, I know. So again, I would recommend revisit topic 15, like later after the class, if you, yeah, like say here, like error probability, and then how we're making the conclusions, decisions. It's coming from topic 15, okay? So you can review that as you see fit. Here, I guess I will just repeat my question one more time. We did compute a p-value of 0.0075, okay? It is small, okay? Meaning that out of like 10,000 simulations that I've done, I only see 75 of them as extreme as my data, right? And then that gives me a probability of 0.0075, okay? So my question is, if I use a 5% cutoff point as the threshold, then I will see that my 0.0075 is smaller than that 5%, right? So if I'm using that as a decision-making threshold, then I'm going to reject my null because it's smaller than that threshold. Okay, so this is saying if I'm coming back all the way to the experiment in the first place, right? We're trying to figure out the causality, right? We're trying to figure out whether BTA is effective or not. Okay, so in this case, we reject the null at the 5% level, meaning that we're going to favor the alternative, right? Meaning that the treatment is indeed effective. Okay, yeah, so with that in mind, if now I use a more stringent cutoff point, 1%, do I reject or do not? I do not reject based on this 0.0075, using a 1% threshold. Thoughts? Maybe in the chat, or if you feel like speaking up, feel free. Or if you think it's better to go back to a breakout room, happy to do that as well.
We'd still reject, right? Because it would be lower than the 1% level.
Yeah, thanks, Mike. Yeah, and thank Joram in the chat as well. Yeah, so in this case, it is going to be still reject, right? Because it's still also smaller than, yeah, thanks, Matt. It's reject. Yeah, yeah, we're going to reject because it's also smaller than 0.01. Okay, so again, if you go back to, and then we come up with the same decision, right? Like say we reject the null, the effect, like the treatment, the BTA medication is effective, okay? And things like that. So, but I just want to say that like the 1% cutoff, 5% cutoff, if you go back to topic 15, there's some like historical account of why this numbers came up in the first place and stuff like that. Okay, so if you're curious and then want to get a review about them as well. But for us, honestly, if you're taking a stats course, maybe not at Vassar, but like maybe in high school, for example, if people do not explain too much about why small p-value results in a rejection, then I think hopefully in this course, you start to see like why that is the case, okay? Especially we're doing it from the simulation point of view, right? Like we are actually simulating statistic, like the histogram that we're doing onto the null, right? Then when you are simulating onto the null, what you're doing, you're assuming that the null is true, right? You're assuming that the null is true, this is what I get. And I get it for 10,000 different times, right? And then I'm able to compute the p-value given the definition that we know. So I'm just hoping to convey this idea that the p-value is really a probability, okay? If it's really small, it tells me that I have more evidence towards my alternative because the small p-value shows me that it's very unlikely to observe something as extreme as my data if the null is true. Right? If the p-value is relatively large, then it tells me that I do have some evidence in favor of my null hypothesis, okay? Because under the assumption that my null is true, it is likely, overall likely, I guess, to see something as extreme as my observed data. Okay, so all of this is driven by, we come up with the two hypotheses, and in particular, the null hypothesis is what we assume is true when we're computing p-value, okay? And then, so the general rationale over here is that, well, I have my null, I have my alternative, right? I'm simulating under the null. If I have so much evidence saying that after I simulate under the null and then do the p-value calculation, if I have a lot of evidence in favor of the null, I do not reject it, right? If I have a lot of evidence in favor of the alternative, I'm going to reject it. P-value is really just something that we try to quantify how we make the decision, okay? And then of course, I guess in some way it was good that when in the first round, I asked the questions, people were a little confused because I think you guys were all thinking instead of like, oh, p-value is small, so I'm going to reject, okay? In a lot of cases, like that's sort of kind of like a recipe that people follow, okay? But I really hope that from this course and this few lectures in a row, that it's going to be like very clear to you all that indeed we are rejecting, right, the null hypothesis if p-value is small, because that gives us evidence more towards the alternative, okay? And it's because we're simulating under the null, and then so under the assumption that the null is true, if I have a small p-value, that shows me that it's very unlikely to see something as extreme as my data, okay? And then that is what we mean by evidence against the null. Alrighty, make sense overall, hopefully. I know this is probably like getting longer than we, at least I thought would be, but I think it's good that people are reacting, and then if you're confused, feel free just to let me know, and then we can always, and Jason of course as well, that we can always pause a little bit and then go over it one more time. And like I said, I think all of those like hypothesis testing framework gonna be persistent throughout the rest of the semester. Okay, so the more that you see it, I think the more that you're going to get more familiar with all of this, and then hopefully any remaining concerns you still have can be resolved. Okay. All right. Feel free to leave me messages, and I will now